Hello everyone, this will be the last installment of the series of lecture videos for chapter 11. And in this last video, we are going to cover the rest of the learning outcomes, which are basically the mathematical part of the chapter. And among this, the toughest will be learning outcome G, which is the requirement to derive how the pressure exerted by an ideal gas is related to the root mean square speed of the molecules. Then after that, we will be discussing how the average K of the ideal gas is related to the absolute temperature. So now for kinetic theory of the gases. Well, so far we have talked about the ideal gas equation, PV equals to nRT, and with that equation, we basically have a fairly good idea of how pressure, volume, and temperature affects the state of the ideal gas. So basically, we have the macroscopic idea of how ideal gas work. However, we still lack the understanding of the microscopic behavior at the molecular level of the ideal gas. So basically, the kinetic theory attempts to relate the microscopic behavior of the gas with the microscopic properties of the molecule. So for this part, there are actually a total of 6 assumptions made. So these are the 6 assumptions, and you actually need to memorize all 6 of them. You can actually be asked in A level to list down the assumptions, and 1 mark is actually given for each assumptions. So at the very least, the first few are always the most important, especially the first one, where the intermolecular forces are negligible except during a collision. This particular one is so important that we are going to repeat it again in the next chapter, chapter 12. So now in the next few slides, we'll be applying these assumptions to derive an equation to explain how the pressure is affected by the density of the gas and the root mean square speed of its molecule. So once again, memorize them. So for this section of the lecture notes, we are going to attempt to derive the pressure on the container due to the ideal gas using the 6 assumptions that we were discussing just now. So basically, these two complicated looking equations are the one that we'll be trying to derive. So to introduce the formula, P refers to the pressure, of course, and then N refers to the number of molecules. Small m, it actually refers to the mass per molecule. So do not mistaken it as the mass of the whole gas. No, it does not. Small m actually refers to the mass per molecule. And then V refers to the volume. And then we have this funny looking notation. Basically, these two brackets, it actually means average or the mean value. And then C refers to the speed. So we have C squared. So the bracket of the C square actually refers to the mean square speed or the average square speed of the molecules. And then on the right hand side, we have P equals to 1/3 rho C square. So basically rho refers to the density of the gas. How you can correlate the two equations is that we have the number of molecules multiplied by the mass per molecule. That gives me the mass of the whole gas. So the mass of the whole gas divided by volume, basically that gives me the density of the gas. These two equations are really important, and the fact that you need to derive them tells you this is actually important formula for this chapter. But the good thing is the one on the left hand side is actually given in the list of formula. So if you actually understand how N, M, and V are related, basically this is referring to the density of the gas. You should also be able to derive this equation easily from the given formula. However, still, even though this is given in the list of formula, you are still expected to be able to derive them because I can give you a 6-mark question purely just to derive this equation. So now, to derive the pressure formula exerted on the container wall, the steps can look really complicated and intimidating. But if you actually just look at the big picture, it basically just follows 3 key steps. So step 1, we always start simple. So we'll start by looking at only one molecule and how this single molecule collides with a wall in a single dimensional motion. So by single dimensional motion, what I'm referring to is just that the molecule is moving left and right, that's all. So to find the pressure, we use an equation that we have learned since O-level, force over area. And basically force is equal to the rate of change of momentum of the molecule, something that we have learned in chapter 3, basically Newton's second law. So once we are done looking at this one single molecule, we'll move on to step 2 and generalize the pressure equation to n number of molecules. And then in step 3, we will relax the assumption of the molecule moving only in the singular dimensional motion, but extend the equation to a 3-dimensional motion, that's all. So essentially, to derive the pressure formula, what we are going to do is just look at one molecule moving in 1-dimensional motion, then generalize it to n molecules, and then finally relax the assumption and make it a 3-dimensional motion. So now for step 1, to find the pressure on a wall due to one single molecule moving with speed cx in the x direction, let us start with one thought experiment. So imagine I have a really long container where the right hand side actually stretches to infinity and I have a wall A on the left hand side. And I actually have one molecule, just one of them, where the mass is m and having a velocity cx traveling towards wall A. You will collide with the wall, and the collision is actually an elastic collision. So recall that elastic collision is actually one of the 6 key assumptions of the kinetic theories. So after colliding, you actually rebound off. You rebound off wall A, and then what happens next is you'll fly away to the right and never ever returns. Because remember, my right hand side actually stretches to infinity. So now, how would we quantify the pressure acting on wall A when there is only this one molecule hitting the wall A once and then never ever return? So think about this. The pressure should in this case be 0. You must remember pressure is actually an average concept. We rarely or even never talk about what is the instantaneous pressure acting on the wall. In all the time that we are talking about pressure, it is always about the average pressure. And you may be thinking, why are we even discussing this? Well, because the formula for pressure is actually force over area. And to know what force to substitute into the numerator, we need to know what pressure are we actually looking for. So recall, we are actually looking for the average pressure. So the force that we should be substitute, should it be the instantaneous force, the molecules X on the wall, or should it be the average force, the molecule acting on the wall, considering the frequency of this molecule colliding with the wall? So the answer should be obvious. We should be using the average force by considering how often this molecule will be colliding with the wall and therefore finding the average force in this scenario. So with this understanding, now instead of considering an infinitely long container, we are going to consider the more realistic cubic space of side length L. We are still going to look at only one molecule having the same momentum mcx colliding elastically with wall A, and therefore it will also rebound off with the same magnitude of momentum since it is actually an elastic collision towards the right. Therefore, taking rightwards as positive, the change in momentum of the molecule is equal to 2mcx. Now, we have the change in momentum, and in order to find force, we will need to use the Newton's second law, where Newton's second law tells us that force is actually equal to the change in momentum over time. And this is also actually one of the kinetic theory assumption D, where we assume that the molecules will obey the Newton's law. So go refer to it if you actually need to recall. But for now, in order to find average force, which is the one that we need to find in order to find average pressure, we will need to consider the frequency of the collision, and hence we need to find the time between collision. So basically, the time the molecules will take to move from A to B, wall A to B, and then back to wall A again. So from A to B, and then back to wall A again. So the time between the collision with the same wall A is essentially the total distance from A to B and then back to A again divided by the velocity. So essentially, the total distance will be L times 2, so therefore 2L divided by the velocity of the particle, which is basically Cx, since it is having a collision with wall A, an elastic collision. So we have found everything that we need. We have the change in momentum of the molecules, which is actually 2mcx, and also we have found the time between the collision with the same wall A, which is 2L over Cx. So therefore, we can use Newton's second law. So the force on the molecule will use the change in momentum of the molecule divided by time, and therefore getting us mcx squared over L. But since we are trying to find the pressure on the wall, we need to find the force on the wall, which we can find using Newton's third law. The force on the molecule will be exactly equal to the force on wall A. So therefore, to find pressure, we will be using pressure equals to force on the wall divided by area of the wall, which is basically the force mcx squared over L divided by L squared, which is the area of the wall. So therefore giving us mcx squared over L cubed. Some of you may already be thinking, to find the average force, why are we only considering the duration between collision, and why are we not adding in the duration of the molecules during collision with the wall, i.e. the total time that the molecule is spent interacting with wall A itself? And this is really because, once again, one of the assumptions of the kinetic theory is that the duration of the collision is negligible. Duration of the collision is negligible compared to the time interval between the collision. So therefore, there is really no need to add in the duration during collision. So now we have already found the pressure on the wall due to one molecule. We can now move on to step 2, where we extend the problem into n molecules with perhaps each molecule realistically moving at slightly different speed and hence momentum. And the total pressure due to n molecules is really just the sum of the pressure due to each single molecule. So therefore we have mcx1 squared over L cubed plus mcx2 squared over L cubed plus 2 mcxn squared over L cubed. So basically what we need to do next is basically just to factorize m and L cubed out of the equation, and then therefore we can get this expression. And this expression can be further simplified into this particular expression where you see this funny notation once again. So this funny notation once again is really just the average square speed. And how do we find any average in mathematics? Is basically just to sum every square speed together, divide by the number of them, n. So essentially, my average square speed is basically the sum of all the individual square speed divided by n of them. And then if you work backward, you can eventually get this equation from this complicated equation. Now, this is also known as the mean square speed in the x direction. And at the same time, even though we have relaxed the assumption to solve for all molecules having different speed, but right now they are still assumed to be moving in one horizontal direction. We have not extended it into 3 dimensions, which is what we are going to do next. So for step 3, we are going to extend the equation into 3 dimensions. So basically, because in reality, not all the particles will move in the horizontal direction, they can be moving in any direction 3-dimensionally. So essentially, we have this expanded picture where you see all these molecules are still moving in a singular dimension left-right direction. And then when we relax the assumption to allow the molecules to move in any random 3-dimensional motion, then this molecule may possibly then be moving this way as shown. So basically you still have MC1, which is still moving in the left-right direction in the x direction. And then you have this MC3 here, which is moving in some diagonal direction in a horizontal plane. And this velocity c can then be broken down into the x and y component. Some x component and then the y component. And then finally, you still have this MC2, okay, where it is truly 3-dimensional and the velocity can be now broken down into 3 components, the x component, the y component, and then finally the z component. So basically in step 3, a molecule with velocity c may be moving in any random direction. And this random direction can always be broken down into 3 components, basically the cx, the cy, and cz. And as you can see from this diagram, we can find the resultant c by applying the Pythagoras theorem 2 times. Basically using cx and cy, we can get this diagonal. And using this diagonal and cz, by applying Pythagoras theorem once again, we can find c. Another way to look at it is velocity c is basically the vector sum of the component along the x direction, y direction, and z direction, cx, cy, cz respectively, and are basically related by the Pythagoras theorem. C squared is equals to cx squared plus cy squared plus cz squared. And now if you want to find the average of all the molecule, taking the average, the mean square speed is basically c squared, mean square speed c squared equals to cx squared plus cy squared plus cz squared on average as well. And for large number of gas molecules moving randomly, there should be no preference of the motion to be in any of the x, y, or z direction. So essentially, we are going to assume for all the molecules, we are going to assume that the motion is going to be uniformly distributed in all directions. So what we mean here is, if let's say there is one particular molecule that has a higher weightage in the cx component, definitely you will be able to find another molecule that has the same heavier weightage in the cy component, or another molecule as heavy a weightage in the cz component. So this means that the value of the mean square speed should be equal for the x, y, and z direction, i.e. cs square average must be equals to cy square average must be also equals to cz square average. So therefore, c square average equals to the sum of the average of x, y, and z direction is essentially equals to 3 times cx square average. So therefore, we have cx square average to be equals to 1/3 of c square average. So from before, our total pressure was given nm cx square average over L cubed. So now we can substitute 1/3 c square average into this equation, and therefore we get 1/3 nm c square average over L cube, where n times m is basically the total mass of the gas molecule, because once again recall, m refers to the mass of one molecule. And then since I have n molecules of them, basically n times m give me the total mass of the gas molecule. And then L cube is basically the volume of the cube, the cuboid space. So therefore, we'll let L cube be V. We will therefore be able to derive pressure, can be written as 1/3 nmc squared over V, or 1/3 rho c squared. Okay, where rho is equal to the density of the gas, which is basically the total mass of the gas molecule divided by the volume of the cube, nm over V. So basically right now we have already derived what we set out to derive in the first place, the equation to relate the pressure of the gas to the density and mean square speed of the molecule. Okay, so this derivation is actually required for the purpose of A level, so please make sure you understand the derivation completely. This is probably going to be the most difficult derivation that is actually required for the purpose of A level. So make sure you understand them. Otherwise, please make sure you ask your tutor to go through this again in class. Finally, just to give you another way to understand things. So originally we have this equation, P is equals to nm cx squared over L cube, okay, where we are assuming all the n molecules are moving in only the x direction. But as we relax the assumption to allow three-dimensional motion, as we mentioned just now as well, the molecule should then be uniformly distributed to be moving in any direction. So therefore, logically, all these n molecules that was originally moving only in the x direction, I should therefore be able to think of it this way as 1/3 of them to be moving in x direction, 1/3 of them to be in y direction, and then 1/3 of them to be in the z direction. Okay, so therefore, what we can do is therefore change n into 1/3 n, and then let cx squared right now to be moving in any random direction. And this is also one way I can actually correlate the two equations. Okay. However, that being said, this second method is really just to help you to see things in another way, but the proper derivation should still follow exactly to the notes. We are finally in the last part of the theory for chapter 11. So for this section, we are going to show how the average kinetic energy of the molecules of an ideal gas is actually proportional to its thermodynamic temperature. The good thing here is the derivation is actually not required. So basically what you need to do is to memorize the formula. But at the same time, if you're memorizing something, you need to know what you're memorizing. So please highlight the keyword average. The word average here is really very important. And so you may be wondering, why is this word so important? If you actually recall at the very start of the chapter, we have highlighted that the larger the mass, the higher the internal energy. You will also come to realize in the next chapter that the internal energy of an ideal gas is essentially the total Ke of the molecules. So therefore, if let's say we are comparing between two ideal gas clouds, maybe one with a smaller amount of ideal gas, okay, the one with the smaller amount of ideal gas should actually have lower total internal energy, which also means that it should have lower total Ke. So you can compare here, the smaller cloud here, okay, should have a lower total Ke than the larger amount of ideal gas cloud. But the average Ke per molecule will still be the same as long as the absolute temperature is the same. Okay, so if let's say I'm just looking at molecular level, okay, the average Ke of each molecule, whether is it at the smaller cloud or is it at the larger cloud, as long as the temperature is the same, they will have the same average Ke per molecule. In fact, I don't even care what type of ideal gas they are. Even if let's say one gas have a larger molecular mass, okay, so let's say the smaller gas cloud actually contains molecules with a larger molecular mass, okay, I don't even care that as long as the temperature is the same, the average Ke will still be the same, okay, and the way to prove it is to actually use the formula that we have proven just now. So basically, since we have proven P is equal to 1/3 nm average C squared over V, okay, all I'm going to do is to manipulate this formula. So I bring V to the left hand side, I have PV equals to 1/3 nm average C squared. And if you recall, PV for an ideal gas is basically NKT, okay. Why I use NKT in this case is because I have the number of molecules. I just want to use a formula with the number of molecules as well, because the next step that I'm going to do is I'm going to cancel them away. Okay, so I'll be cancelling the n away and then bring 3 to the left hand side. So you can see that I have 3kt equals to m average c squared. And if I were to multiply half, okay, the value half on both sides, what do we get? We will get the average Ke per molecule, because I'll get half m c squared, c average squared, okay, c squared average. And that will actually be equivalent to the equation 3 over 2 kt. And the total Ke for n molecules, all I need to do is to multiply n. So I have half nm c squared, and that will give me 3 over 2 nkt. So essentially, just to differentiate the two formula, the first one, 3 over 2 kt, is only the average Ke per molecule, whereas 3 over 2 nkt is actually the total Ke for n molecules of ideal gas. Okay, and at the same time, you should be aware that the energy, the Ke equals to 3 over 2 kt, is actually a formula that is given in the list of formulae. Okay, so it is listed under mean translational Ke of a molecule of an ideal gas. E equals to 3 over 2 kt. So now moving on, once again, average Ke per molecule is equals to 3 over 2 kt. Total Ke of n molecules is equals to 3 over 2 nkt. So basically, you can see that because 3 over 2 k is actually a constant, so that proved to me that the average Ke is actually proportional to the temperature. So temperature can now be seen as a measure of the average translational Ke due to the random motion of the molecules. And the Ke due to non-random motion is not considered. You may be thinking, what? What the heck is Ke due to random motion and Ke due to non-random motion? Okay, so let's take for example, if let's say I have a container, inside is gas molecules. All these gas molecules must be moving randomly in all directions. Okay, think about your Brownian motion from O-level. The Ke due to this random motion is what is proportional to the absolute temperature. But imagine if I am to throw this whole container to the left at high speed. Then other than the random motion, all the molecules are also having some non-random motion. Every molecule has this additional speed horizontally towards the left. Every one has them all moving towards the left, nothing random about it. Okay, so basically, this non-random part has nothing to do with the absolute temperature, but the random portion is still going to be proportional to the temperature. So basically, all that is what I mean by random and non-random motion. And then finally, the Ke for non-ideal and real gas is also proportional to the temperature. Now, of course, the formula may not exactly be the same as 3 over 2 kt, but the relationship that Ke proportional to T is still applicable though. The same relationship can also be expressed in terms of number of moles. So basically, average Ke for 1 mole of gas is basically 3 over 2 RT. The total Ke for n moles of gas is basically 3 over 2 nRT. So basically, these are the last 4 important equations that you must know for this chapter. However, there are also some limitations when applying this formula. But first and foremost, correct this particular typo in your lecture note. The formula should be half small mc squared equals to 3 over 2 kt instead of half big mc squared equals to 3 over 2 RT. Anyway, based on this equation, what it suggests is that at absolute zero, the average K of the gas molecule should be zero, which means they are at absolute rest. However, this will actually contradict a more fundamental principle in quantum theory in chapter 19, which states that the molecule will still have a minimum energy at absolute zero. But basically, what it is saying is that you absolutely have no freaking idea what the heck is happening, but it is okay. Just remember for now, okay, that the absolute zero does not mean zero energy. What it means is absolute zero is the temperature at which all substances have a minimum internal energy, not zero energy. And for now, for root mean square speed, it is essentially just the root of the mean square speed. That's all. Okay, the concept of root mean square speed, or RMS in short, is more important when it comes to chapter 18, alternating current. But for now, the computation is really simple, and we will illustrate this with a few examples later. Also, while it has the same unit as speed, root mean square speed is not the same as mean speed. Okay, and once again, you'll see this when we are discussing about the examples later. The idea here is basically that in any gas with so many molecules, it is impossible that all of them are traveling at one particular speed only. Okay, So basically, each molecules are traveling at different speed, just like how we relax the assumption in step 2 when deriving the pressure formula. So essentially, they have a range of speed, but we can calculate a single root mean square speed. As for the food for thoughts, can we assign temperature to a single gas molecule since half mc squared is equals to 3/2 kT? Well, the answer is no, because temperature expresses the collective property of all the molecules. And what does it mean? Like I said, all the molecules are traveling at all different speeds, but the temperature of the whole volume of gas is at one particular temperature. So the temperature is not assigned to any particular molecule, but instead to the whole volume of gas. Furthermore, the equation is relating to average Ke, which involves averaging the speed of all molecules. Hence, the equation is not a concept relating to any particular molecule, it involves the whole gas. Alright, as this particular lecture video has already gotten to be a little bit long, I'll therefore leave the solving of the rest of the examples officially as the next lecture lesson. If, however, you find that you still have the time and energy to just finish off the rest of the examples, do feel free to continue watching the next video where I'll go through discussing the rest of the examples. I think it would be good to do so, as it can actually give some finality and conclusion to the chapter nicely. However, if otherwise you feel that you really cannot tahan for another 8 minutes or so, then feel free to leave it as part of the next lecture. Alright then, okay, thanks, bye!
Did you get any of that?
Sure, Bo,
Understand?
your online source of
Interesting physics lecture.